Okay, Year 12, I'm going to go over the work for exercise 14.06, and it's called, or has to deal with, the empirical rule. Now, in the last exercise, we used a table to calculate the probabilities within a certain range of data. And now that we're talking about the normal distribution, so we're talking about a normal distribution here, we can use a thing called the empirical rule, which is down here. Now, the empirical rule comes from integrating these equations and working out the area underneath them. And the empirical rule states that in any normal distribution, now you can draw three separate graphs, but I think you're better off just doing this. Drawing yourself a pretty symmetrical bell curve and going, all right, so if this is a normal distribution, I'm going to have my mean here. And because we're using continuous data, we're going to use the Greek symbols. So that's the mean. And if I go one standard deviation, and I'll use the Greek symbol, either side of the mean, it's symmetrical. Two standard deviations. And notice on the left-hand side that they're negative. So negative standard deviation, that just means it's below the mean. And finally, three standard deviations. Now, we don't often go beyond three standard deviations. And the reason being that 99.7% of the data is between three standard deviations. So what have we got now? Well, here, within one standard deviation, 68%. It's approximately, it's not exactly. Two standard deviations, 95%. And three standard deviations contains 99.7%. I'm going to show you how that's calculated in a minute. So how do we apply this? Well, if we're given a set of data and we're told that it fits a normal distribution and we're given the standard deviation, we can calculate the percentages of data within a certain standard deviation. And also, once we can do that, if the normal data, the normal distribution, is a probability density function, well then we can calculate the probability of finding that. And the normal distribution is a probability distribution function. So let's go down here to some of the questions. Question 1, we just did. Question 2. So we're going to do question 2. Now my suggestion to you, let's make it visual. Make this work visual. So draw yourself. You don't have to draw the curve, you can if you want. Split it, draw yourself a line, put your average here. And it says that the average in question 2 is 15. And then go 1 above, and the standard deviation is 1.5, so that's 16.5. 2 above, that'll be 18. And 3 above, 3 standard deviations, 19.5. Note, I just added 1.5 each time. To go down, I subtract 1.5. So I get 13.5. 2, I get 12. Take another 1.5 off. And then take another one off, and I get 10.5. Now, usually they'll ask you a variety of questions in this. But in question 2, they just say, well, what percentage is there? And you know it's a normal distribution. They must state that the data is normally distributed. That's 68%. Between 12 and 18, 95%. We're essentially doing the same thing we did before. And 10.5 and 19.5 is 99.5%. 99.7%. Now, how else can they ask you this? Well, they can ask you a whole range of different things. And by the way, if you really wanted to, you could have drawn the curve. That's a dodgy one. Drawn the curve. But you don't need to. You just need to know the range of the data. So I'm going to jump now to question 4. So normally distributed with a mean of 18, standard deviation of 2. Well, this is easy. Remember, we're only really going to go 3. So our mean is 18. And then we go 2 up, 20. Another 2 up, 22. And the third one, 24. We go 2 down, 16. Another 2, 14. And the last 2, 12. Now, 16 and 20. So here's A, 16 and 20. Well, that's between here and here. We know that's 68%. So 16 to 20 is 68%. Well, that's easy. That's like the other ones. B, 14 and 22. Well, that's like the other ones as well. 14 to 22 is here to here. So 14 to 22 is 95%. C, 12 to 24. Well, that's the same as before. 12 to 24 is within 3. Standard deviation is 99.7. Now, in D, I start getting a bit tricky. 16 and 18. 16 to 18. Well, if I look at 16 to 18, I'll use this one. Oops. There's 16 to 20. Now remember, this data is symmetrical, and we know that's 68%. So 16 to 18 is a half of 68%, which equals 34%. And I'm just going to make sure that I've got this right because I've got the answers on my other computer. And we're going to question 4. And we got 34%. I was pretty sure I was right anyway. E. Well, what are they asking E? 18 and 24. Well, 18 to 24. Well, that's half of 3 standard deviations. So 18 to 24 is a half of 99.7. And it's good to write it, even though we know. And a half of 99.7, 49.85. Still, these are pretty easy. 12 and 22. Now this is where you've got to be a little bit smart. So from 12 to 22. Now what I want you to do is think of these as 2 areas. You could think, oh, it's 2 standard deviations plus that last little third. Don't think of it like that. Think of it like a half of the 99.7 plus a half of this bit, which is the 95. So how do we write that? So 12 to 18 is a half times 99.7. And 18 to 22 is a half of 95. So the total equals a half times 99.7 plus a half times 95, which gives me 97.35%. which means, and that's how tricky they'll get it. That's as tough as you need to get. In question 5, the answers are similar, or the questions are similar. Now, I want to now talk about what NASA have said. So this is this stuff that we've been doing. So the normal distribution. Identify numerical and graphical properties of data normally distributed. Yeah, all these sorts of things we do. Calculate the probabilities, quantiles, we did that, of the normal distribution. Recognise features, graph, probability, density function, normal distribution with a mean and a standard deviation. Use standard, okay. Now, we haven't done z-scores yet, that's next. But I want to look at the third last dot point here. Use collected data to illustrate the empirical rules for normally distributed random variables. And there's a question in the sample paper where they show the third part of this dot point. And that's what I'm worried about, and that's what we're going to do in one of our lessons in the future. We're going to work out or confirm the probability distribution using the areas, the trapezoidal rule, under a normally distributed function that they give to us. But let's have a look at these other ones. So apply the empirical rule to a variety of problems. We've been doing that. But sketch the function y equals e to the negative x squared and the probability density function for the normal distribution using technology. Well, here we go. So here I've graphed y equals e to the negative x squared. And if I look at that, zoom in on that, you can see it forms a beautiful bell-shaped curve. But this is not a probability density function, and I'll tell you why. So I'm just going to get in here, and I'll call that fx. And now I'm going to integrate that. Now if you just type in int, it gives you that. And because it's about 0, I'll just go from, I don't know, -3 to +3 f of x dx. And you can see that the area between 3 and -3 is 1.772. So that's not a problem. That even though that function draws what we seem to think, or is a normal curve, but it's not a probability density function. So what did they say? Well, they said, so sketch the graph of f of x e to the negative x squared. That's okay, we did that. Use technology, good on it. It looks like a normal distribution, but it's not a probability density function for the normal distribution. We've got to do some other stuff with that. So see this one here, f of x equals 1 over, this, and that's a symbol for the standard deviation, times the square root of 2 pi, e to the power of negative x minus the mean all squared over 2 times the standard deviation squared. Well, I did it. And you can see here, I couldn't find the sigma or the Greek. I couldn't use the Greek letters, and I couldn't use x bar. I suppose I could have. Maybe the Desmos would allow me to do that. So I used S to stand for the standard deviation, and I used A to stand for the mean. And what I've done here is I've typed in this equation, and if I, come on, I'll use this thing. Even if I move it, right, you can see that it moves. And if I zoom in, you can see it there. And if I play with the standard deviation, it gets, get back here. That makes it really flat. But if I get it here, look what happens. Oh, it goes up. And it's still a normal distribution. Now, if I find the area, now I tried to go the integral of the area under the curve, f of x, because I've got it there above, between infinity and negative infinity, hoping that it would give me 1, but it must have integer limits. So I said, all right, well, I'll go from 100 to negative 100. And look, it equals 1. So it's probably not exactly 1, but it's so close to 1 that it's given that variable. But that's not even the best part. The best part is this. Check this out. And this is exactly what we're doing. So if we go to Desmos, I'm going to just go in and get another one. And if you type in normal list, hold on, I've got it on my other computer, I'm just getting up. I've got to get the right terminology. Normal list, and I go righto. It plots it straight away. And it says, what do you want the average to be? So let's go back. Let's go back to the question we just did, which was 4. So it was a mean of 18 and a standard deviation of 2. Oh, this is so good. Watch this. So we'll go 18, 2. Oh, get out. Get back here. 18, 2. And I'll zoom in immediately. There it is. Now, get this. This is so cool. If I click here, find the cumulative probability via the cumulative distribution function. If I click that, it shades it. And it does do it from negative infinity to infinity. But let's go back to the questions we were talking about. Let's go back to the 2 harder ones, which were questions 4, E and F. So 18 to 24. So if I go back and I type in 18 to 24, or even if 22, I think the question was, it calculates at 47.7. And what did we get? Oh, it was 18 to 24. So we'll go back. 18 to 24. I'll go back there. 49.85. Let's go back to the graph. 49.865. So because when you're using the empirical rule, you're using approximations that have been rounded, this is more accurate. And you can get anything you want. You can go from any number you want. You don't even have to go from standard deviations. We could go from 11 to 24, and there it is. We could go from 11 to 20, and it shows us and it gives it to us. This is a very powerful tool and very useful. And I think that's what they mean in NESA when they say use technology. So there are those two things. There is the graph of f of x equals e to the minus x squared. It's not a probability distribution function. However, if we put it in that form, we get a probability distribution function. But this, if you type in normal dist, you can type in any mean, any standard deviation. You can find the cumulative probability via the cumulative distribution function, and it calculates it for you. Okay, good luck with that.